So we just went through the relatively complicated process of calculating the F values and the P values for a two-way and ANOVA. And what we saw was that while it was a little bit more involved, it was basically the same process as working with a one-way ANOVA or a linear regression. We calculated these F values, which was the ratio of the explained to the unexplained variance. We saw where those F values fell on the distribution of F under the null hypothesis, i.e. that the data is all just randomly generated, and if the F value, if it was very unlikely to get an F value that size or larger, then we would say that the P value was small. Now we're going to talk about t-tests. T-tests are a bit simpler, all right? In fact, people often start with t-tests because they're so simple. However, t-tests are actually kind of the odd one out in everything we've talked about. Though what we're going to see is that they're not really. So what is a t-test? All right. So one of the first t-tests I could find published in the biomedical literature is also a very important clinical trial. It's the first clinical trial of benzodiazepine. Now you might not be familiar with what a benzodiazepine is, but Xanax is a benzodiazepine. Um, Valium is a benzodiazepine. There's a whole family of these drugs that make you sleepy, make you calm. And they have a collection of uses, slightly less uses than they used to have, because now we don't like to give them to people because people like taking them too much. But still, very useful drug to have in the pharmacy. And this was it being used on neurotic patients, people suffering from anxiety. So this is also an important study because it was one of the first studies to use a so-called objective scoring mechanism, right? So the doctors didn't just say, I think this guy's better. They said, fill out this form. You know, if you're doing this, you've got a 3. If you're pulling your hair out, you got a 5. Whatever they went through, I can't remember it right now. And then they gave each patient a score. They gave them a score before they tried Librium and after they tried Librium. And here, higher is better. So if they get a higher score, they've improved a lot. So what we want to know is, if they had repeated this for an infinite number of subjects, would the mean of this sample be different from 0? Which is what it's saying is this sample significantly different from 0? This is a one sample t-test. How does a one sample t-test work? Well, you calculate t much in the same way um, as you do with an F, but it's not quite the same. So you take the mean of your sample, you subtract it from your theoretical mean, the number you want to know that it's different from, in this case 0, so you just get the mean, and then you divide it by the square root of the standard deviation squared, i.e. the variance, divided by n. Okay, and you go through that, and in this case you get t equals 11.78. And then you do what we're familiar with. You see what is the distribution of t under the null hypothesis. And there we see it there. This is what the t distribution looks like when there is no effect. Again, most of the time t is close to 0 because most of the time this value at the top is 0 because under the null hypothesis, our data has the mean of 0, right? Where there is no effect. When we're modeling this, the null hypothesis, there is no effect. We get it most of the time as 0 up here, so it doesn't matter what we divide it by, our t is mostly 0. And then we do the same thing. Well, what are the chances of getting a t value of 11, which is just the area under the curve of this distribution? As you can see, it goes way off the edge of the graph. The likelihood of this is basically 0, so we conclude that there is a real effect. Now, with a slight tweak, we can change this to a two-sample t-test, which is asking, are these two samples drawn from different populations? The equation's a little bit more complicated, but it's sort of conceptually the same. Instead of we do the difference from a theoretical mean, we do the difference of our two sample means. And again, we divide it by something that's basically the standard deviation divided by the n size. You have to do something complicated because your two groups could have slightly different variances. But, if the standard deviations are identical, then this works out to be exactly the same as the previous equation. And we calculate t, and we again go, what is the distribution of t if there was no difference between these groups? And t-tests are great, right? I love t-tests. I always say, if you can make your experiment give you a result that you can use a t-test to understand, you're doing well, right? They're just there to see if the means of two samples are statistically different, or as I said in a one sample t-test, if one sample mean is statistically different from a hypothetical value. So, is blood pressure different between a treated and an untreated group? Is tumor size different between a wild type and a knockout? Or you might say, is weight change in response to a drug different from zero? This is something called a paired t-test. Paired t-tests are actually one sampled t-test where you do the control, that you do the before minus the after for each subject. That gives you the change, right? And then you do a one sample t-test of that change from zero, because if the mean of the change is zero, then there's been no effect.